Welcome to Crypto 101, a first principles jargon-free course on blockchain and its impact on financial services. We are currently in the process of learning about a popular decentralized finance application called Uniswap. In this lesson, we will continue with our discussion of this decentralized exchange. In the previous lesson, we covered 4 of the 5 concepts needed to understand Uniswap. In this lesson, we will continue learning about the final concept of concentrated liquidity. We will learn about concentrated liquidity from 2 perspectives. We will begin with the liquidity provider's perspective. Then, we will move to the trader's perspective. To understand concentrated liquidity from the liquidity provider's perspective, we will break this lesson into 4 concepts. First, we will begin with the concept of infinite liquidity. Then we will learn about the problem of low capital efficiency, which exists within the infinite liquidity paradigm. Then, we will learn what is concentrated liquidity is and how it solves the problem of low capital efficiency. Next, we will cover the concept of price range. Consider the constant product market maker graph between Ether and Tether. The constant K equals 1000 for this liquidity pool. Assume that there are 2 tokens of Ether and 500 tokens of Tether in this liquidity pool. Note that while the graph line cuts off visually on this chart, it extends to infinity on either side. At the extremes of this price curve, the quantity of one token is close to 0 and quantity of the other token is infinity. The current equilibrium of this liquidity pool is at point P. The price of a marginal token at point P is 1 Ether equals 250 Tether. We know that there are 2 Ether tokens and 500 Tether tokens in this liquidity pool. Let us take 2 random points on this curve. Point Q and point R. How many of the Ether and Tether tokens are existing between points Q and R? We will begin from the equilibrium point P. First, we will determine the quantity of Ether between point P and point R. If a trader wishes to sell 300 units of Tether to reach point R, he is going to get 0.75 Ether in return to maintain equilibrium. Hence, between point P and R, we can deduce that there are 0.75 units of Ether. What about between point P and Q? We know there cannot be any Ether to the left of point P. This is because a trader who wants an equilibrium at point Q is seeking to add Ether to the liquidity pool and receive Tether from the pool. There is no need to hold any Ether to the left of point P. Next, we will determine how many Tether tokens are there in the range between points Q and R. We will again begin from the equilibrium point P. First, we will determine the quantity of Tether between point P and point Q. If a trader wishes to sell 0.5 units of Ether to reach point Q, he is going to get 100 Tether in return to maintain equilibrium. Hence, between point P and Q, we can deduce that there are 100 units of Tether. What about between point P and R? By the same logic we discussed in the previous slide, there is no Tether to the right of point P. We can now answer the original question. How many tokens of each type are available between point Q and point R? The answer is 0.75 Ether and 100 Tether. We can now reflect on the term infinite liquidity. There were 2 Ether tokens and 500 Tether tokens in the liquidity pool. The starting point on the curve was point P, where the ratio of the 2 token quantities reflected the relative price at which the 2 tokens were trading outside Uniswap. If someone wants to buy Ether from the pool, their orders will be fulfilled along the points on the price curve to the right of point P. The total inventory of 2 Ether tokens is spread across the price line that extends to infinity. On the left of point P, there are no Ether tokens. If there were, then traders would simply buy them and bring Uniswap back to equilibrium in point P. Similarly, on the left, the 500 tokens of Tether are spread across infinity. Version 2 of Uniswap worked on the infinite liquidity paradigm, where the tokens deposited by liquidity providers were distributed across the constant product market maker graph. However, this resulted in the problem of low capital efficiency. Next, we will learn about this issue. Consider a Uniswap liquidity pool pair consisting of 1000 Tether tokens and 1000 DAI tokens. Tether and DAI are both stable coins. At this point, the price of both tokens is assumed to be exactly $1 each in centralized exchanges. Hence, in the liquidity pool, there are equal quantities of both tokens. Both these are stable coins and their relative price ranges between 90 cents and $1.10 in the open market. Point Q and R represent the 2 states. Based on our previous illustration, we can conclude that there are 91 Tether tokens distributed along the curve between point P and R. Also, there are 100 DAI tokens distributed between point P and Q. But this also means there are 889 Tether tokens to the right of point Q and there are 900 DAI tokens to the left of point R. Next, we will reflect on why this is a problem. Here is a question. When will traders trade against this liquidity pool so that the new equilibrium is to the right of point R or the left of point Q? The answer is only when the relative price of the two tokens in other markets is outside the 90 cents to $1.10 range. While it is theoretically feasible, such an event is highly unlikely because the two stablecoins are highly correlated. Hence, of the 1,000 Tether tokens deposited by the liquidity provider, nearly 90% remains unutilized. Same occurs with DAI. We will now review two scenarios. One is called infinite liquidity and the second is called concentrated liquidity. Alice and Bob are two liquidity providers. Alice contributes 1,000 tokens of Tether and DAI each across the entire spectrum of possible price points. This is infinite liquidity. Bob contributes only about 100 units of Tether and DAI across what he expects the price range of the two tokens to be. Next, we will review the impact of these two options. We will begin with Alice. The beginning point is P, where the price of Tether and DAI are equal. Tether appreciates in centralized exchanges to the point that 1 Tether equals 1.1 DAI. Hence, a trader processes a trade against the liquidity pool. The trader sells 100 DAI to the pool and gets 91 Tether tokens in return. The trading fees he pays is 30 basis points of the quantity of tokens sold. In this case, it is 30 DAI. Alice receives 30 DAI. Next, let us see how Bob is doing. The exact same thing occurs with Bob. Bob receives 30 DAI. We can now see what the problem with infinite liquidity is. Alice and Bob earn the same fees, but Bob deploys 10% of the capital to get the same return. In infinite liquidity, a lot of the liquidity would be sitting idle and not earning any trading fees. In concentrated liquidity, the pool contributor can earn a higher amount of trading fees relative to capital investment. The term concentrated liquidity refers to the provision of inventory in a defined price range. Instead of liquidity being provided across an infinite price range, it is concentrated in a narrower band. Is there a downside to concentrated liquidity? Next, we will answer this question. Consider what happens when there is increased volatility in the market. The price of Tether appreciates to the point that 1 Tether is equal to 1.2 DAI. A trader sells to the pool 200 DAI. In return, the trader must receive 167 Tether, but Bob has contributed only 100 Tether tokens to the pool. Hence, Bob's tokens are effectively removed from the pool for the purpose of this trade and Bob earns no fees on the trade. In version 2 of Uniswap, everyone was forced to provide liquidity across all price ranges, whereas in version 3, liquidity providers specify the price range in which they wish their tokens to be available for swap. In version 3 of Uniswap, the liquidity provider defines his target price range and provides liquidity only between the specified price range. In this example, at point Q, the liquidity provider has 100% of his balances in DAI tokens. If a trader wished to sell more Tether to the liquidity pool in exchange for DAI, the LP does not have any more DAI tokens to give back to the trader. At point R, the LP has 100% of his balances in DAI. If anyone wanted to sell DAI to this pool in exchange of more Ether, the LP will not have any more Tether tokens to give. Next, we will learn how price range affects trading fees. Consider Alice and Bob, who each contribute Ether and Tether tokens. They contributed to the pool at different times, when the exchange rate between the two tokens were different. Alice contributed 10 Ether and 10,000 Tether tokens. Bob contributed 1 Ether and 1,500 Tether tokens. Assume at a given time, the total pool K is 100 million. In version 3 of Uniswap, Alice and Bob are required to specify their target price range. Let us take an extreme example. Alice selects the price range in Zone A while Bob selects Zone B. It so happens that the price of the two tokens in centralized exchanges exclusively swing in the upper and lower bounds of Zone B, hence, all trades occur in Zone B. Alice does not earn any trading fees while Bob earns a pro rata share of every trade that occurred in Zone B. In version 2 of Uniswap, Alice and Bob were entitled to a share of the fees earned by the liquidity pool. This share was the percentage of pool tokens they had at any point of time. The fees were added to their token balances, which in turn increased the quantum of pool tokens they had. This had the same effect as compound interest. In version 3 of Uniswap, the fees is allocated only to those LPs who participated in the pricing range of the trade. This is not a simple pro rata allocation of the global pool. For the same reason, fees are not added to the token balances but credited separately. It is as though in version 2, the bank was adding interest to your bank balance while in version 3, the bank is simply accruing interest earned as a separate line item. In version 3 of Uniswap, each liquidity provider is assigned a non-fungible token to represent their contribution to the liquidity pool. Each NFT represents a unique combination of token quantities and desired price range. Fee is allocated to the NFT based on the fees generated from all token trades that meet the NFT parameters. The NFT can be traded like any other token. Pool tokens in version 2 were fungible. All that mattered was how many tokens you contributed. In version 3, each token is unique as every LP can set her own price range. In version 2, the pool tokens entitled the liquidity provider to a share of the fees indirectly via capitalization of the fees to the deposited token reserves, thus having a compounding effect over time. In version 3, the fees is recorded against the pool token directly, instead of being capitalized to the liquidity pool. So far, we have discussed concentrated liquidity from the perspective of an LP. Next, we will see how this impacts the trader. Consider a liquidity pool with 1 Ether token and 1,000 Tether tokens. The current price is represented by line P. In Uniswap version 2, K would be calculated as 1,000 and the price of a trade was determined by keeping K constant. However, this formula does not work in Uniswap version 3, since the tokens are only provided within a specified price range. The mathematics behind Uniswap v3 is more complex and is out of scope for this course. However, we will cover the intuition behind the math in v3. Consider a brand new liquidity pool. There is only one liquidity provider who has seeded the pool with 1 Ether and 1,000 Tether tokens. Remember that the first token depositor can contribute tokens in any proportion she wants. Hence the current price of the token is 1 Ether to 1,000 tokens. So far, this is exactly like Uniswap v2. The big change in v3 is that there is a price range. The liquidity provider has established a range between point Q and R. Based on our prior discussions, we know that at point Q, there is no Tether left, and at point R, there is no Ether left. We can create an alternative line that replicates the original price curve but now has finite boundaries across the two axes. Next, we will learn the significance of this second price curve. In Uniswap version 2, the price of a trade is determined by the formula of the blue line, namely the constant product market maker function. In Uniswap version 3, the price of a trade is determined by the formula of the green line. The two formula are in reality the same, with version 2 representing an instance of the formula where points Q and R reside at infinity. However, solving the version 3 iteration of this formula requires more complex mathematics and is out of scope of this lesson. Let us recap what we have learnt so far about the swap price in Uniswap version 3. First, the marginal price of a token for the first swap every processed against a pool is equal to the ratio of quantities in which the token pair was first seeded by a liquidity provider. This is identical to version 2. Second, the actual price at which the first swap will be executed is determined by a variant of the constant product market maker function, which applies to scenarios where the liquidity has been bound within a price range. Next, we will learn about an additional element of complexity in Uniswap. Let point P represent the current market price of a token on Uniswap. The price is set at 1 Ether equals 1,000 Tether. Point R represents the end point of a liquidity provider's price range where 1 Ether equals 2,000 Tether. In the external market, the price is shifted to 1 Ether being 3,000 Tether. The trader now wishes to reach a point to the right of R. However, beyond point R, the liquidity provider has no more Ether to give. Luckily, there is another liquidity provider whose price range is exactly contiguous. The new equilibrium is formed between points S and T. Point P1 is the new marginal price. From this example, we can note that the trader in Uniswap version 3 not only jumps between points within a price range but jumps across price ranges. We can also conclude that the current market price in Uniswap version 3 is not a simple ratio of the two token quantities in the pool's reserves. The global liquidity curve in Uniswap v3 is actually an aggregation of multiple smaller range-bound curves. There was a simplification in the previous example, where we showed the price ranges to be contiguous. But, in reality, price ranges are overlapping. For instance, 1,000 liquidity providers may choose the range between point A and B, while another 100 may choose between point C and D. In fact, it is possible that there is no liquidity at all within certain ranges on the curve. This gives you an idea why the mathematics behind the constant product market maker function, as applied to Uniswap v3, is far more complicated than v2. But hopefully, you have obtained an intuitive understanding of what is happening behind the scenes. We can now summarize some observations on current price in Uniswap version 3. Like in version 2, the current price is the price at which a marginal token can be bought. The first current price quoted by a pool is simply the ratio of the two token quantities in the pool. The subsequent values of the current price are determined by slippage, either within a price range or across price ranges. The current market price in Uniswap version 3 is not a simple ratio of the two token quantities in the pool's reserves. This is because the price curve in version 3 is actually an aggregation of multiple overlapping price range bound curves. This brings us to an end to the discussion of the 5 concepts central to Uniswap. We have come to the end of this lesson on Uniswap. Our discussion so far has been theoretical. In the next lesson, we will navigate to the Uniswap app and use it. But before proceeding, review the summary of the existing lesson.